Alright, so in this video we go over section 6.8 exponential growth and decay models and Newton's law of cooling, which are applications of exponential and logarithmic equations. So the first model that we are going to discuss is one example dealing with exponential growth. So we have a situation in which the colony of bacteria that grows according to the law of uninhibited growth is modeled by the function n of t equals 100 e to the 0.045 t, where n is measured in grams and t is measured in days. That is, this function is a function of amount n that depends on t time. So we're going to answer a few questions about the situation using this function right here. So letter A, determine the initial amount of bacteria. What do we mean by initial amount? Initial here means when t equals to 0. That's what it means. So I'm going to write and evaluate it at 0 equals 100 e to the 0.045 rather, times the amount 0, which I'm going to plug in here. Okay, so this is what I'm going to get. Whatever number like 0.045 times 0, that's 0. So I'm going to have 100 essentially e to the 0. However, this e to the 0, keep in mind that any quantity to the 0 power always equals 1, giving me 100 times 1, which is 100. However, because in this case we are having context going on, we need to add the unit, so grams. All right, that's the final answer for part A. Part B, what is the growth rate of the bacteria? Okay, that is given by the number that multiplies the variable t in the exponential part. Observe this number. So in this case, the generic model related to the given equation or function rather, it's n of t equals an initial e to the kt, where k is it's going to give us the growth rate. We put it as a decimal on the formula on the function, but when they ask us for the growth rate, we need to change that into decimal form. That is 4.5. So that means that that with every day that happens, the growth, the bacteria colony gets larger by 4.5% every day. What is the population after 5 days? Well, very similar to letter A, but instead of plugging in a 0, we are going to plug in a 5. And all we do is plug this in the graphing calculator, and I get approximately 125.2 grams. Okay. So that's what we get. So in this case, well, depending on when you're doing the homework, depending on the number of decimal places that you are asked, so that's what we're gonna get. Now the question is, how long will it take for the population to reach 140 grams? And notice here I got a larger number than the initial, because in this case it's growth. The population is getting bigger every time. Now let's see, how long will it take for the population to reach 140 grams? Well, In this case, we're not plugging 144t. We are actually setting the function 100 e to the 0.045 t, set that equal to 140. And then from here, solve the equation for t. And we have solved equations like this in our previous sections. So the first thing we do is divide both sides by 100. All right, I get this canceled, and I get e to the 0.045 t equals 1.4. All right, so now we need to get rid of this exponential. In order to do that, we take ln to both sides. Take ln on one side, take ln on the other as well. And here ln cancels out with the exponential, leaving us with 0.045 t equals ln of 1.4. And dividing both sides by 0.05 gives us the value of t. Cancel this out, and t equals whatever we get from this calculation using the graphing calculator, and I get approximately 7.5 days in this case. All right. What is the doubling time for the population? So, all right, so now they're asking us when will the population become twice as much. Okay, so keep in mind that the initial population is 100. So twice will be, so doubling will be n of t equals to 0. Okay, so they're asking us for the time for which n equals to 100. So I'm going to set 100 e to the 0.045 t equals to 100. And then I'm going to solve these for t just the same way we did it earlier. Divide both sides by 100 in order to get this done. Cancelled. 200 divided by 100, I get a 2, and e to the 0.045 t. So ln to both sides, and cancel ln with e. So 0.045 t equals ln of 2, and we simply divide both sides by 0.045 to get t by itself, which is our main goal. And using a calculator, I get t equals approximately 15.4 days. So this is one first example. Let's look at another example. Right, so a colony bacteria increases according to the uninhibited growth, which again, let's write this down. That's n of t equals some initial amount e to the k t. All right, if n is the number of cells and t is the time in hours, express n as a function of t. So all we have to do is just rewrite this in a very generic form, and if n of t equals n initial e to the k t, precisely what I had in black right there. All right, so if the number of bacteria doubles in 3 hours, find a function that gives the number of cells in the culture. Well, look at this type of question this time. It's not giving us any information about K. It's not giving us any information about the initial amount. We don't have pretty much anything yet. Yet using some experimental observations, it is observed that the number of bacteria doubles in 3 hours. We are going to use this information to find K, which is the the constant of the proportion constant, right? That means, what is that? What does that mean? Well, when t equals 3, n initial becomes 2 times n initial. That is, it doubles. In function notation, though, which is very important to see it this way, it means that n of 3 equals to n initial. All right, so this is what I'm going to do. I'm going to start writing the formula again. N of t equals n initial e to the k t. So I'm going to plug in 3 for t. Plug in 3, so because after 3 hours the number of bacteria doubles. But what do we know about n of 3? Isn't it 2 times n initial? E to the 3k. Alright, so we are going to solve this equation for k. NO again is the initial amount. This subscript is like 0 or initial. Okay, so cancel, 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 cancel. And we get e to the 3k equals to 2. So now to solve for this, we undo the exponential by taking ln to both sides. Okay, so here ln with e cancel each other, and we get 3k by itself, which is ln of 2. And finally, k is simply ln of 2 divided by 3, which is approximately 0.23 105. Well, I'm going to take a few decimals, but I'm going to cut it at the end. I'm just going to take these 5 decimals. Right, what did we do here? Divide both sides by 3. All right. Now there is another question. How long will it take for the size of the colony to triple? All right. So this will be very similar to the previous part. Okay, how long? That's the question now is how long. It's about time. The size of the colony to triple. In other words, to triple requires that n becomes 3n initial. In the previous case, we did doubling, which is 2 initial. Now this time, it's n the one that will become actually no initial symbol here. Okay, so it will become 3 times as much. So I'm gonna set n initial e to the, well, in this case I know the value for k, which is 0.023, no, 0.20. Let me erase this real quick. 0.23 105. that equals to 3 times the triple of the initial. And again, I'm going to solve this by first dividing both sides by an initial. Cancel, 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 cancel. And e to the 0.23105 equals to 3. Now we need to take ln to both sides to get rid of this exponential. And cancel, cancel. And actually I forgot the t, and the t right there. So we get 0.23105 t equals ln of 3. And all we do is just divide by 0.23105. Cancel, cancel, and in this case t will be approximately 4.755 hours if we use a calculator to simplify this quantity. So that was another example of how to apply exponential functions. Let's do now decay. And for decay, well, the function is going to look somewhat similar, because as we discussed at the beginning, almost at the beginning of the chapter, so n in the n of t equals n initial e to the negative kt. So the sign of the exponential dictates whether this exponential model will model decay or a growth. So in this case, we are going to deal with a different situation now. So we have that traces of burned wood along with an ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14, which is a special chemical element that is used to date archaeological objects, to tell how old are they in millions of years, not just thousands, but actually millions of years. The half-life of carbon-14 is 5,600 years, approximately. When was the tree cut and burned? All right, so let's find out how are we going to use this formula. Okay, so we're going to start by writing n of t equals n initial e to the negative kt. Okay, we're going to forget about this 1.67% for a second. And we're going to use this piece of information right here. The half-life is 5,600 years, right? Sorry about that. So this means that if n is evaluated at 5,600, we get half of this, not double like the previous examples. So in this case, because it's half-life is the amount that has to happen in order for a substance, an initial substance, to become half of it. So it will become 1/2 of whatever initial amount is. It doesn't matter. Notice in this case we are not given the original amount. In fact, for a situation like this, we are not going to know the original amount, because this object found was from millions of years ago or thousands of years ago. So it's practically impossible to know how much was in there initially. All right, so we're going to use this as a starting point to get, in fact, our K, which is the decay constant. So N evaluated at 5600. It's going to give us this quantity, 1/2 NO. All right. And then from here, we are going to solve the exponential equation for K. So first of all, let's divide both sides by an initial. Okay. So e to the negative 5600k equals 1/2. And taking the length of both sides, we get negative 5600, okay, actually, equals ln of 1/2. All right, so if we solve for k over here, we are going to get the following. I'm going to get ln of 1/2 divided by negative 5600 and k is approximately 0.0000124. Okay, and well, in this case we get a positive value, but it's going to adopt a negative sign once we put it in here. All right. Now that we have n of t equals an initial e to the negative this value 0.000124 t. So now they're asking us when was the tree cut and burned. All right, knowing that after a while, well, after a long time now, 1.67% of the original amount was found. That means that with 1.67% present, this means that an initial has become 0.0167 of its initial. Well, now then the amount n that we have is 0.067. Keep in mind that we write percentages as decimals when we put them in formulas. So 0.0167 n initial equals n initial e to the negative 0.000124 t. So when we divide again by n initial, what do we get? Well, we get this n initials cancel, n initials canceled, and e to the negative 0.000124, t equals 0.0167. So again, to get rid of this exponential, we apply the ln to both sides to get negative 0.000124 t equals ln of 0.0167 and divide both sides by negative 0.000124. Negative 0.000124. And using a calculator, we should get approximately 33,003 years, which is how this long has been since the tree was burned and cut. All right, so let's move on to the next example, to the next topic. The next topic is Newton's law of cooling, which is a very fun application, another very fun application of exponential functions and logarithmic equations as well, both of them. In this case, well, we have some object, so the temperature U of a heated object at a given time t can be modeled by this function, where big T is the constant temperature of the surrounding medium, U in U sub 0 or U naught is the initial temperature of the heated object, and K is a negative constant. The reason why this is a negative constant is because when we heat an object, let's say we heat a pizza, we put it in the oven, we take it out of the oven to the room temperature, which is this big T, it's a constant, and what's going to happen to the temperature is going to go down, it's going to cool. That's why it's a negative constant. So let's do an example. An object is heated to 100 degrees Celsius, and then is allowed to cool in a room whose air temperature is 30 degrees Celsius. All right, that's all we know. Okay, so let's see. If the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be? 550 degrees Celsius. All right, so let's first of all label all our givens. Okay, so in this case, the temperature of the surroundings, okay, or the temperature of the room, which is 30 degrees, this is going to be our big T. While this 100 Celsius is nothing but our U sub 0. So let's first of all write the mathematical model with this given information. So U of T equals big T plus U initial minus big T e to the k T. Given that we know that big T is 30 plus 100 minus 30 e to the k T, which is 30 plus 70 e to the k T. All right. Now, let's see, if the temperature of the object is 80 when 5 minutes have elapsed, okay, what will be the temperature? When will its temperature be 50 degrees Celsius? Okay, so how are we going to get this done. So in this case, this is U and this is T. So I'm going to write 80 equals 30 plus 70 e to the k times 5, which is this 5 is the time, and this U is the temperature that it's given as the data. So that's I'm going to subtract 30 and get 70 e to the 5k equals 80 minus 30, that's a 50. And then I'm going to solve for, I'm going to divide 70 on both sides, and e to the 5k will be equals to 5/7. And again, in order to get rid of the exponential, we take ln to both sides. Cancel, cancel, and we get 5k equals to ln of 5/7, and divide both sides by 5 to get k equals approximately, using decimals, I get negative 0.0673. Okay, where do I get that? Well, divide both sides by 5. Plug this in the calculator, you should get this as decimals. So what are we going to have so far? So this formula that we have here, which by the way I'm going to highlight or put it in a box, because this formula is our starting point, if you will. Okay. Now it will become with some k. All right, so now U of t equals 30 plus 70 e to the k, which is negative 0.0673 t. Now they're asking us when will the temperature will be 50. Okay, so that means this is another U whose t is unknown. We are going to find out. So this will be 50 equals to 30 plus 70 e to the negative 0.0673 t. So I'm going to subtract 30 on both sides, giving me a 20. 70 e to the negative 0.0673 t equals to 20. Let me make this look nicer. And then we solve for the exponential term before we solve for t. And we do that by dividing both sides by 70. Now that we have the exponential term by itself, take ln to both sides and cancel the ln with the exponential. Negative 0.0673 t equals ln of 20 divided by negative 0.0673. Well, it's actually, I did a silly mistake here. This should be ln of 20 over 70. ln of 20 over 70. All right. Or you can actually get rid of the zeros, it's fine. And we should get over here t equals or rather approximately 18.6 minutes. All right. So that's the approximate answer to some decimal places, one decimal place, two decimal places, depending on what the homework is asking us for. Determine the elapsed time before the temperature of the object is 35 minutes. All right, so it's going to be very similar to this. So we know that U of t equals 30 plus 70 e to the negative 0.0673 t. So we're going to set this equals to 35. So subtract 30 to both sides, we get 70 e to the negative 0.0673 t equals 5. That is minus 30, minus 30. And divide both sides by 70. So all this is just solving exponential equations, just identifying where are we going to put our given, if it's u or if it's t. Cancel, cancel, e to the negative 0.0673t equals 5 over 70. Even though it can be reduced, let's just leave it like this. And then take ln to both sides. Okay. Cancel ln with e. And that's going to give us negative 0.0673t equals ln of 5 over 70. And all we do is finally divide both sides by 0.0673. And that's going to give us t equals, or rather approximately, approximately 39.2 minutes. And there's one more piece of information that didn't fit in here, so I'm just going to use the back side of the page for a part C. So part C is, what do you notice about the temperature as time passes? All right, this is going to be a very, very interesting question. So we are going to have the following. All right, so we're going to have, again, let's begin with u of t equals, let's do it first of all the mathematical way, and then we are going to use the context of the situation. So let's see, we have u of t equals to 30 plus 70 e to the negative 0.0673t. All right, so what is going to happen here? So if we rewrite this in the following form, 70 divided by e to the negative 0, e to the actually positive, not negative, 0.0673t. Well, think about large values of t. That is, time is going to pass on, right? That's going to pass. this t is going to be bigger. So what happens when we divide by a huge number? So this t is going to get big times its decimal. Well, I mean, maybe this exponential is going to get bigger and bigger, so the denominator gets bigger. So if we divide by a huge number, eventually this term is going to go to 0. So u of t will be 30 for large values of t. All right. Now consider the object that is out of the that it's being heated and then put it at a room temperature. For example, a pizza. So you put a pizza inside of the oven. It gets cooked and all that. Then you pull the pizza out of the oven. Leave the pizza for a large period of time at room temperature. What's going to happen to the pizza? Well, the pizza is going to get it's going to cool. Eventually, it's going to reach room temperature. And this is a good place to quit. I'll see you on the next video.